one will stand, right? So. Yeah, this is a mess, man. It's not a desktop.
I see you do the same thing as I do. Put stuff into a text file and then just save them, and you end up with a bunch of files with no useful name.
Actually started using Evernote. A lot better.
Yeah.
Oh, desktop is a big mess for me. I mean, it's like I can't find things.
Yeah, I've become super reliant on the fact that the search on the Mac works really well.
Yep.
So I can find stuff because I wrote this.
Let's grab a seat. I think we should start. Good morning. Are you guys awake or still like recovering from the morning sleep? Okay, cool. Okay, guys, I guess you guys are having good time at APRICOT. So if not, my promise is we'll have a fireworks in this panel, okay? So this is probably one of the most hot topic in the industry today. And we have 4 distinguished speakers among us. Fujita Tomonori from NTT, Peter Landon from BTI Systems, Eric Choi from Brocade, and Alistair Johnson from Nuage Networks or Alcatel-Lucent. So without wasting any time, I would like to invite Fujita-san on the podium to take us through the Ryu SDN framework. Fujita-san.
Thank you. I'm Fujita from NTT Software Innovation Center. Today I'll talk about the Ryu SDN framework. So today's agenda is what's Ryu, and I'll talk about several use cases. First use case is this is pretty much main topic, and then I'll talk about our future plans. So I don't know how many people here already knows about Ryu, but Ryu is an open source SDN framework we started, I guess 2 years ago, and basically that Ryu is a Python library for SDN. So it's enable you to deploy or program your SDN solution agilely. So it's just a library, not turnkey solution, and it's a licensed Apache 2, and and we have a lot of users already. And we provide several features. So one of is Openflow. We support several versions, and 1.5 is just released last month, and we are working on. And I think most people still use 1.3, but we support tons of versions. And we provide a packet library. That means parsing and building a lot of various protocol wire format. So when you receive the packet on wire, you pass the header and data structure on wire data format, and you can easily visualize and identify whatever you want. And also, when you want to send some packet to someone, you can use Ryu to build a packet, various protocol, IP, TCP, UDP, MPLS, OSPF, whatever protocol. And Ryu also provides some various protocol feature. BGP, so you can use Ryu as a BGP speaker. Speak to existing router or whatever. I'll explain this use case at first use case, and we support VRRP, BFD, or PMP. PMP is BGP management protocol. I can't recall correctly. I'm not sure, but something like that. So, so who use? So we have tons of users, vendors. Fortunately, a lot of users already use Ryu, and top switch vendors and software switch open source software guys, OVS or such, and SDN solution provider, and a lot of users. So this is today's my main topic in my talk. This is a use case, first use case. So integrating cloud and MPLS VPN. This is actually already deployed in NTT Communications production network last year. So Ryu is used. Ryu is used in NTT Communications production network already. So what we did. So basically. So NTT Communications provide cloud service. That's kind of you could imagine Amazon or Google or such cloud service. Basically, you can start virtual machine or something like that. And as you know, NTT Communication also provide VPN. So the problem is. So cloud service, you can change everything one click. I mean, web portal, our customer change the network configuration in cloud service, inside cloud service. So for example, he can create a new virtual network in cloud or something like that. But problem is that's created the virtual network at the cloud was not cannot access via MPLS immediately. We have to change the configuration on a gateway between cloud DC data center between VPN network. That's a problem. And the customer, so after customer change cloud configuration, then customer sending email or something like that, and we got the email and we called our operator, change switch configuration, and that takes, I guess, 1 week or something like that. So it's not cloud service. Not integrated at all. So cloud, everything can change immediately. VPN, not. That's a problem. So we can't tell. that's a sort of problem we try to solve. So we replace the existing gateway between the data center and the VPN. Replacing kind of Openflow switch inside. So we installed our Openflow controller and our BGP implementation inside the box. So it's kind of not common way to deploy the Openflow deployment. I mean, Openflow in general, controller server and switches remotely connected. But in that case, we installed the Openflow controller inside the box. So basically, Openflow used only inside the box. Outside operator doesn't care about Openflow, whatever. Just Openflow used inside API, inside the switch box. So it's kind of not common way, but and we also, as I said, Ryu also support BGP feature. So our BGP implementation speaks to PE. That's of course existing big vendor switches. So we use a BGP, and so these this Openflow boxes, kind of white box switch. What it means, we can install whatever software we want to. I mean, just Linux. And we installed any software we want to. So we change a log format or whatever. So we nicely, that enable us nicely integrated the existing cloud orchestration system. So after this deployment, customer can change cloud configuration. Then these changes immediately to reflected gateway switch. That kind of we connected with our own API via our own API, our cloud orchestration system, and our new switch are connected. So lessons learned. So Ryu, Openflow, and we use, in this use case, we use Openflow and BGP, and Openflow white switch box, white box switch, it's kind of bare metal, no operating system from big vendors. So we running Linux, and we install the BGP and such. We basically implement our own operating system as a switch. So that's kindly easily integrated with the existing infrastructure, cloud or our accounting system or such, or logging system or such system. So here, Openflow is not must. We don't, as I said, Openflow, in this use case, Openflow does not only used inside the box, so nobody care. Just no operator care about Openflow. Just one of southbound protocol. So that doesn't matter. Any other protocol API can be used in this use case. And in this case, so white box switch and Linux operating system running on that box enable this use case. So I'll explain shortly a white box switch. I mean, white switch box normally means merchant silicon plus Linux OS in general, commodity hardware from ODM vendors in Taiwan mostly. And the point is, whatever software you can install, that's a Linux box. That's kind of same as PC server. You can, as I said, you can install your own BGP protocol implementation, and you can also monitoring system, your favorite monitoring. I guess you guys, everybody has a favorite monitoring software for PC servers, so you can use the same software for switches, and you can install. You can easily do automation, Chef or Puppet or such thing. That's a PC. As I said, just a Linux. So no big deal, not big difference with normal servers. So the problem are so big switch vendors. So the question for us, NTT has, so vendors or network vendors provide BGP. So for example, BGP or new features, timely manner. So we have, so market, today's market very, the speed of market is very fast. I mean, vendor provide new feature timely, and switch still support SNMP for monitoring or such feature, but who prefers that? I mean Linux server, who use SNMP to monitoring PC servers? That's a kind of new rich software, new better software exists. So. And you can automate the switch configuration existing system easily. So vendors switches provide only limited API, for example, CLI, of course, and netconf or something like that. But you can't customize big vendor switch software. So it's difficult to integrate your existing system with existing switch from big vendors. That's so white box switch enables such thing. So this is the main use case. So another use case is a BMP server, BGP monitoring protocol. I guess some of big vendors which support this protocol. So basically, this protocol you enable monitor urgent leave-in changes. So before the filter, so you can monitor the changes route before filter. So imagine you could get a notification via email or tweet or whatever notification or your favorite way about unexpected event such as dramatically change route information or such, or strange route information come, or something like that. This is, so we provide such feature. So you could use Ryu to monitor your BGP routers, existing BGP routers. And this is a third use case, SDN IX DOS mitigation. This is a kind of last year, demo that interrupt by internet malfeed. As you see, so basically deploying. This is just demo. So deploying Openflow switch inside the IX, and so when you the customer of AS2 detected some DOS attack from AS outside, then you can configure the Ryu controller, and you can configure the Openflow switch blocked such traffic. So you can block DOS attack from very upper place before come from IX. That's a kind of demo was at last year. So our future plan. Next. So we also, of course, we support Openflow, and as I said, with our experiences, white box has huge potential for us. So we are planning to deploy some software, whatever software necessary for white box switch. So protocol stack, probably mainly BGP and whatever necessary, and so not Openflow. Openflow could be used, but not necessarily. So white box provides several API. One of Openflow or a vendor-specific Silicon API or Linux standard API or something like that. So whatever, these could be chosen depend on your use case. So Openflow, one of API. So not must. So another future plan is we are working on, actually this is already working, we are working on a new Ryu BGP speaker implementation. As I said, we implemented BGP speaker feature for use case 1. That's implemented in Python, of course, but problem is high performance. I mean, IX route server is our use case. So we found a kind of performance problem with such use case. So we tried to develop high performance BGP server. The problem is Python is single thread, so no benefit from multi-core or latest hardware. So we implemented a multi-threaded BGP implementation and much fast. And we implemented new BGP implementation, not Python, a new language, Golang, that's invented by Google and used everywhere, Google deployment, I guess. And so much faster language, program language. So we are working on implementation, and we already, so it's we finished the basic feature. So if you're interested, such BGP implementation, please try. That's please let us know about your thought. That's it.
Any questions for Fujita-san?
Martin Winter, open source routing, NetDev, so I'm working on Quagga. So side question on the BGP, did you consider implementing any FIP compression, like any compression of the FIP table? Because all these white box switches have very small forwarding table normally. So did you implement anything to compress the routing table?
Not yet.
You have any plans on that or working on that part?
Yeah, we still working. So BGP implementation on white box is still we are researching stage. So yeah, I'm not sure what. So compression may be necessary. So we will think about it in the future.
Okay, thank you, Fujita-san. So the next speaker is Peter Landon from BTI Systems, and he'll talk about why operators need optical transport SDN. Peter.
Morning. So I want to take a few minutes and talk about optical transport SDN. Now, a couple of people have mentioned to me that, well, isn't this just a reintroduction of existing protocols like MPLS or SNMP? And there are similarities, but I think there's enough benefit to SDN in general, in particular transport SDN, that it really does warrant an education and discussion. So the focus of the first few releases of Openflow were centered around layer 2 and above, and they had little L1 support. There was mention of optical ports, but that was about it. The optical transport working group within the ONF has been working on a protocol extension spec, which will define the requirements of Openflow for transport networks. So why is it important? Well, here we have an example of an SDN-enabled DC interconnect, data center interconnect. You've got a router connected to a transport box, and maybe you've got a couple of 10 gig links being routed and transported across an optical network. In this configuration, any changes to, without SDN, any changes to the optical transport box would have to be done manually. Now, let's say you want to add some ports from the router to the transport box. Let's say we've added another 100 gig link. Using transport SDN, you could change the modulation format on the transport box from the DP-QPSK that it might be using to a 16 QAM format, effectively doubling the throughput of that optical link. And that could be done automatically through programming of the transport without any interaction or management from the operator. So you might ask, why not just provision this link at 16 QAM, leave it nailed up, and be done with it? If you were to do that across your whole network, it would be a pretty severe impact to your power budget. 16 QAM DSP, at least today, is very power hungry, and if you multiply that across your network, you're going to see a power hit. So the other thing is a vendor lock-in issue. Without SDN in the transport layer, you would need a couple of NMSs here, one for your router, another one for that transport vendor. If you've got another transport vendor, you have a third. You have to manage those, learn them, and by unifying the control plane, it allows you to frees you to deploy the gear of choice and maintain a consistency on the control plane and not have to relearn new NMS systems. Along these same lines, and somewhat related, is FEC that's used on the transport NE. In a coherent system, that might be, you might have a proprietary soft decision FEC, but if you were to use the internal, in the chipset, the hard decision FEC, those are more interoperable and, again, allows a more of a software programmable interface, which can be done, again, automatically. And you have similar, not similar, but sufficient coding gain for a metro reach, let's say. So another aspect that makes transport SDN valuable, well, pulling multiple domains together. SDN allows the use of federated domains. You may have heard or seen these. Basically, the main controller doesn't have to control every NE. So you can have subnetworks under control, and these subnetworks will advertise their capabilities to the upper controller. And in that way, you're extending the efficiency of the network through your underlying controllers, but still maintaining a unified single level of control. So packet optical convergence is another area that SDN can help. Here we have an example of a data center interconnect where some clients are TDM, and some are packet, and some are both. There are vendors today providing converged packet optical solutions, which when combined with SDN control infrastructure allows a more seamless transition from TDM services such as SON at SDN, or SDH rather, to Ethernet offerings, because the control plane is already aware of the capabilities of the port. This is another factor that drives up the value of transport SDN, because without these elements, having an open standard just wouldn't be as valuable. And as a side note, having the programmability on the line side for rates can also reduce your OpEx, because you can utilize a single PEC code across different platforms and vary it based on the needs of the network and the needs of the link. So now we'll go through a couple of use cases. The first one opens up a revenue opportunity for network as a service. By having control of the underlying optical transport network, operators can slice their networks dynamically, creating optical VPNs, which give the customer a view of the network resources and its capabilities like latency and capacity. In doing so, the customer has a different approach towards the network of saying, I want to program it to do what I need, not how I'm going to do it. So he doesn't have to think about programming all the intermediate nodes. He just knows his intent is to have a connection between A and B, and he doesn't care or need to know what's. So the second use case is a little bit different. Here we're talking about dynamic adjustment of adjacencies. In other words, being able to change the bandwidth between points on the fly. Now this is a little bit different than bandwidth on demand, which is getting a lot of attention lately, with good reason. Because in this case, changing the bandwidth is done dynamically. Through programming the controller, it's not a scheduled or calendared bandwidth event. It's done based on flows. So the chart in the corner is somewhat of an eye chart, but basically all it's saying is that peak traffic in America is dominated by streaming or real-time entertainment, movies, etc. This peak traffic can also be described as an elephant flow, and there's a couple of different kinds of elephant flows that you've got. They're based on duration. A streaming movie may be considered medium-term elephant flow, while a transfer of gigabits of data between NASA sites might be described as a long-term elephant flow. These flows can consume bandwidth to the point where they would trample important critical mouse flows that would be happening between the same points. So using SDN, we can deal with these elephant flows in an elegant way, but it depends on a few assumptions. Number one, that you have an overcapacity in the network, whether it's production advance or shared restoration resources. And secondly, that you have a mesh network, maybe a ROADM network or otherwise. Now in this example, let's say you have a data backup that's happening, an elephant flow. So here we have two data centers, data center A on the left, data center B on the right. And we have data center A wanting to perform a VM migration or a backup. And under no SDN controls, traffic shaping will begin, and you'll see a real possibility of trampling of mouse flows when the elephant flow begins. So in the case of SDN control, the controller's aware of the L0 network. It knows it has another path that it can take, and it automatically provisions that, that larger path so that the elephant flow can flow through the excess capacity. As mentioned, it could be a shared protection resource, it could be an overcapacity, but either way, once the elephant flow is completed, that gets torn down automatically, and you've maintained priority traffic. Now I'm going to mention vendor lock-in again because I know this is an important element of SDN in general for operators. And so basically with a unified control plane, you're reducing the number of NMSs that the operator has to maintain, and he then or she has control over the control plane and all of the learning and intellectual property that they've gained from using it. Set may transition somewhat from that of manual entering of CLI commands to one of more of a programmer type of skill set, but it does add value to the operator in having some of that IP within their company and providing them more choice and more options from a hardware point of view. So how does it work? How does transport SDN work? The fundamental difference, obviously, between packets and circuit switched information. With packets, you've got a header that you can examine, match, and use wildcards against. For circuit switch signals, you need another way to identify it. So for OTN or electrical-based signals, we use the signal type, whether it's an OTU1, an OTU2, etc. And if it's location and time in the case of a tributary. For optical wavelengths, we use the location of the frequency spectrum or its channel number. And in the case of adjacency discovery, which may use LLDP for a packet type of flow, transport utilities use out-of-band communication channels such as GCC or DCC or an optical supervisory channel between ROADMs. So at this point, you might be asking yourself, well, this sounds great in theory, but what about in practice? Networks are much more complicated and complex, and you're right. One good example is, or two, OAM and protection switching as activities that need special consideration. For these types of tasks, the ONF has defined, or is in the process of defining, a concept of autonomous functions. Any function that's repetitive, complex, or has a lot of communication between the controller and the data plane is a good candidate for an autonomous function. Timers, dependency on timeliness of the action, again, good candidate for autonomous function. So the current proposal is a reference-based implementation where the autonomous function will be referenced within the match action table. The function itself needs to be autonomous. In other words, it's a monolithic entity. It closely follows a currently defined definition within the standards body. The intent is not to reinvent anything. It's to implement it in exactly the same way that a standard would define it. If we talk about OAM autonomous function specifically, a protocol like netconf could do the configuration of the underlying equipment in the same way that you would do it today. And it's important to emphasize that the autonomous function doesn't define. It's basically referenced and it's abstracted. So a little bit of detail. As I mentioned, the autonomous function will be pre-configured in whatever means you choose. And then the function is associated with the externally configured object and addressed by reference within the match action table. And it's also important to note that the function itself is not accessible. Again, it's abstracted. So one of the first questions gets asked when you're talking about transport SDN is how is it different from GMPLS? And on paper, there are a lot of similarities that can be pointed to, especially if you consider the pure model of GMPLS, which uses a single instance of the protocol across the packet and circuit domains. However, the pure model didn't take off because of the practicalities of organizational boundaries and prohibiting of information across them. It increases the load on the underlying protocols to distribute the link information for both packet and the transport layer. So you're back to where you started. So what has found favor and has been used instructively for SDN is the IETF overlay model, which was formalized by the ITU as ASON, or asynchronously, or automatically switched optical networks. But this methodology still separates the IP layer and the transport layer with requests for service made across the unis within the network. This propagates the use of vendor proprietary control solutions for the transport layer with still no way to request transport services dynamically. So again, by abstracting the underlying forwarding plane using distributed system techniques and eliminating vendor islands, the control plane complexity is reduced to the point where it may actually have a chance of getting implemented across a wide scale. So a couple of concrete examples on what I've seen from operators doing right now with SDN and how it's helping. I found it surprising to learn that some tier 1 operators were and are using spreadsheets to map router ports to transport network element ports. And while it does sound crazy in this day and age, there are some good reasons for it. When a transport layer box or NE is used in a transparent fashion, just encapsulating Ethernet, it's not terminating the MAC. It doesn't terminate actually anything. It's just putting the whole Ethernet frame into an OTN container. So there's no opportunity to run LLDP or some kind of automatic protocol to resolve port connections. So it results in a manual method of maintaining these connections. So SDN's helping in this way because the higher level controller has obviously knowledge of both ports, and there is a construct to maintain the names of the ports and can also help in debugging of misconnections. Finally, have to talk about bandwidth on demand because what presentation is complete without it. So what we see here is it's again kind of small, but at the network diagram on the top left and right you've got CSPs, and on the bottom left and right you've got a couple of customers. This looks like a typical network diagram, but the main difference is the connectivity to a specific CSP is only enabled when needed. The customer has a portal that can enable that link on demand. And so the end result for the operator is a more efficient network because the bandwidth isn't nailed up, and you get a form of stat muxing in essentially utilizing the bandwidth only when needed. And in this way, you get a more efficient network, and it's cheaper. And the customer is happier because they get to most likely have a lower cost point or even have access to the increased bandwidth that they may not have been able to get if they had to buy the link for a continuous bandwidth. So in summary, Transport SDN lowers the operational expenses through reduced procedures and unified multi-layer control. And CapEx is lowered by homogenizing the physical network and introducing software control. You open up some new business opportunities with network slicing and optical VPNs, and again, simplifies management, getting rid of your manual spreadsheets on your L1, L0 connections. And that's it.
Any questions for Peter?
Yeah, so the ONF is actually taking some action there and trying to define some standard APIs for the optical gear. You know, it's hard things don't move quickly at the hardware level. Vendors that want to implement SDN at layer 0 and 1, you know, have to deal with their equipment and their legacy equipment. So what we see happening is APIs, Openflow, being used to communicate with like an open daylight controller, using an open daylight controller to talk through APIs on the vendor equipment, so that you know you've got your existing equipment with open APIs. The SDN controller, as long as you've got a well-defined set of APIs, which is what the ONF is working on, you can use one SDN controller then across multiple vendors' equipment. So it kind of proposes the APIs that the vendors will use. But again, I mean, setting up an IP address for the box should be something that, yes, I agree, should be more simple. Okay, thanks.
Thanks, Peter. So the next presenter is Choi from Brocade, and he'll talk about implementing MPLS with Openflow. Eric.
Hi, good afternoon. Good morning. So my name is Eric. I'm from Brocade, Product Management. So there are a few things I want to talk about in these presentations. First of all, I would like to talk about why I select this topic and why I think this topic is relevant to a service provider like you. And then I will talk about how MPLS is supposed to work with Openflow, and then a problem that you're going to see and how we work around this. So then I will share with you some of the questions that my customer have and you probably have on the topic of MPLS and Openflow. And finally, I would conclude my slides. So it goes without saying that server and networks are inseparable. So you will have, like, without networks, servers compute resources will be unreachable and will be of low use to anyone. And without, a server attached to the networks, then there will be low traffic driving it, then it's just useless. So as you know, like nowadays, that you have so many server virtualizations, then you will see that it's no longer tied to a physical locations. So moving forward, we will see more and more application, we may not know where and when this application might be, and also it will happen the same thing for the network. So network service we may not be able to know when and where the network service is needed. So we think that network service moving forward need to be virtualized the same way like the servers, and will not be tied to a certain locations. So to speed up the provisioning of the service and the creation of the service. Okay, unfortunately, there are problems with network infrastructures built based on the legacy network architectures. So, like for example, a report from telco tier 1 support.com. So it talked about like the average lead time for a tier 1 service provider in US to turn on service is 30 days. So this lead time is huge, right? When you compare this to the like a couple of minutes that are needed by like Amazon AWS to provision the cloud service to this customer, right? So on the other hand, like maybe a couple of weeks ago in Landon, we are seeing like an operator called M-Lite. So which is a WAN operator in US. They were saying that like with SDN and Oscar management software, they were able to actually provision the circuit, reduce the provisioning time of the circuit from 5 days to just 5 minutes. And if they want to like provision the same circuit across different domain, then it will take in the past it would take 12 days, and now it will just take 5 minutes. So, and also Google's, right? A year ago, they were saying that like the internet, the GKL's internet has migrated to SDN. After they moved to SDN, then they were seeing like the linearization to raise from 50% to 100% with a packet. So if we look at these two examples a little bit deeper, so this actually are like service providers or the networks are making use of are building their SDN WAN virtualization application based on like the construct of VLAN and IP tunnels, right? And but as you know, like service provider, from service provider point of view, VLAN and IP tunnel is not going to be scalable in the multi-tenant service provider environment. So that's why we believe that like for service provider to create SDN-based WAN virtualizations, we believe that MPLS is needed. So because MPLS is a protocol, that is the technology that has been proven to be very scalable in the service provider networks. So I think you guys have may have seen it before, but I would like to take a moment so as to set the stage. So basically, on the left-hand side, you have like how the legacy networks look like. So you have like all the devices and managed vertically as a silos. So meaning that you have vendor A equipment managed by the vendor A EMS and MS have its own set of API and CLI. And you have vendor B have its own set of element management system, and vendor C and so on and so forth. So with this setting, basically, you can assume that it is very difficult for you to to provision end-to-end circuit or to monitor how the circuit work like end-to-end, right? So it's because of these silos, right? Every equipment are managed in their own silos. So now with SDN, basically what we're trying to do is that we're trying to collectively manage all the network devices from different vendors by a set of Openflow controllers or a cluster of Openflow controllers through open standard and through some open API. So it will allow it will provide the necessary abstractions and also system-wide view to the application in the application layer, so that you can actually build a unified application layer management layer for monitoring, management, and control, right? So, and obviously for this architecture to work, then the open control layer is very critical, right? So it has to be very open, right? And by open, it means it's not only means that you need to have open sub interface to manage the device in the loft, in the south. You also need it's not just about having open interface for the loft so that application can be written to make use of the APIs on the controller. It means open source controller, right? Because this is open with open source controller, you can encourage open source open community developers to develop application based on it and to promote interoperability. So this is a key part of the SDN architectures. So based on these SDN architectures, basically we can build various different kind of SDN applications. So going back to the topic of how to implement MPLS using Openflow. So basically MPLS is available starting to support in Openflow starting from 1.1. And there are some more enhancements in 1.3. So with Openflow, you can basically use MPLS as actions and use MPLS as a matching conditions. So in this example, you can basically create rules, so whereby you match on the incoming traffic based on the layer 2 or the layer 3 informations, and based on that, you can push different kind of labels onto it, right? You can insert the labels there, and then on the transit node, then you can also match on the labels, and then depends on your use case, you can try to push another one or swap the label, and so on and so forth. On the egress, you can say, I pop the labels and send it out to a certain interface. So this is all supported in the Openflow. So now, as the number of ingress node and egress node increase, so you will have then the number to scale the number of Openflow entry in the core, then you need to have 2 labels, just like what you have in the Signal to MPLS applications. So in that case, you will have the outer label as a transport label and the inner label as the service label. So in that case, you will have maybe the first node inserting maybe 2 labels, one for transport and one for egress, and along the path, then you will try to pop and swap the labels along the path. So one of the problems that actually it all worked fine in one of our customer case. So until they found out one thing, right? This is the problem that you're going to see is that for MPLS label lookup to work, basically the ether type had to change. So that means that if you want to have if the transit node want to do an MPLS lookup in the transit node, then the ingress node, before they after they insert the MPLS label to the ingress frame, the egress the ether type needs to be changed to 8847, right? And the problem with this is that on the egress, then basically the ether type will be lost on the egress, right? So, and there is all around, right? The way around is to having a different circuit, different labels for different traffic type. So maybe in this example, you have different one label for LDP, and one label for IP, one label for ARP, right? It works in the enterprise environment, but it will never work in the service provider environment where the traffic type or the ingress traffic is not known, right? So then there's a problem here, right? So before we talk about the solution for that, so I would like to, take a look at how Signal MPLS application deal with that. So basically, assuming that we want to create layer 2 circuit from point A to point B, so basically there will be some signaling between the ingress and the egress node, and then finally the egress node will select one labels from the layer 2 VPN range and advertise to the ingress node. So when the ingress node see these labels, then what you do is that it will try to, like, of course, insert the label. But this time is not just insert a label to the user frame. What it will do is, like, it will create a new layer 2 header, and then append the 2 labels, and encapsulate the entire user frame into it, and send it across to the egress, right? And finally, when the frame reach egress, because the egress node know that label Y in the diagram is basically coming from the layer 2 VPN space, then it will just, like, before forwarded to the algo interface, then it will just take out the entire layer 2 frame and send it across. So this is how it works for, like, a signal MPLS applications. So now, how are we going to do it in case of the Openflow MPLS, right? So the goal here is not to have any proprietary extension, so as to make sure that the existing controller can be used. So the idea here is, like, we would like to define 2 range, right, for the MPLS forwarding on both application layer and the device layer, and the network device layer, such that for the first range, so push the labels means, like, insert, push and pop labels means, like, inserting and removing header from the ingress user frame. Like, in case of, like, for the second label range, pushing labels means creating a new header and insert the labels, and append the label and the entire layer 2 user frame to it. Popping a labels means, taking the MPLS payload entities and send it like a layer 2 frame out. Okay? So using this method, basically we can, as you can see, we can retain the layer 2 header information entities on the egress side, right? Without creating any proprietary extension to the Openflow protocol. So this slide talks about how it works with, like, a U controller, so standard-based Openflow controllers. So there is a simple application where it will make use of the RESTful API of the U controller to push labels onto the Openflow device. So on the egress, so you will have, like, maybe standard RESTful API from the U controller. So you will have, like, a match, and for the packet coming from port 50 and with the V100, and then you can you push 2 labels. And one labels is, like, from the number default range, the range number 1, and which is, like, 368929, and the second range is 49999. So these are, like, range from the transport label range, and the second range is from the layer 2 label range. So as the frame is sending across, so on the egress, basically we will match on what we call the label from the layer 2 VPN range, and from there, because the egress knows that this label is from the layer 2 VPN range. So before it forwarded to the egress interface, which is in this case is port 50 again, so it will just maybe take the payload and send it out like a layer 2 frame. So this is how the whole thing will work in case, like, for one of the customer that want to retain the layer 2 header information as the traffic is sending across the SDN networks. So there are some question that our customer used to have, like, when we talk about MPLS and Openflow. One of the obvious one is how the fast failover, the fast reroute or reroute happens in that case. So there are two ways to do it. Like, one is slower, and the other one is faster. So the slower one is the slower solution for that is that you create 2 entry with the same matching conditions, but different forwarding actions. So in that case, maybe if you refer to the diagram, what we want to achieve is that we want to be able to forward the traffic. By default, it is forwarded out maybe E1-1. And in case that interface fail, then we will forward it to Ethernet port 1-2, right? So in that case, you put like two entry there with different priority. So by default, it match like if you send labels like 1,000 to the device, then you will forward to like port 11, right? Now, assuming that port 11 goes away, then then the device needs to signal to the controller and application, and from there the application and controller will then remove this entry from the tables, so that maybe the policy at priority 101 will take effect, and then traffic will be forwarded. Subsequent traffic will be forwarded through the port 12. So this method works, but it is slow because it needs to consult with the control layers when reroute is needed. The other method that will work here is to make use of construct called port group in Openflow. So with port group, basically you can put multiple egress port within the port group, and you can define the port group to be operate in a failover mode. So where like only one port will be active at the time. So in that case, maybe you want to achieve the same thing. So maybe port 11 within the port group 1 will be the primary interface. In case the primary interface go down, so port 12 will be active. So this all done automatically, like without going through the control layer, right? So in that case, you just need to like create a port group, like that consists of this algo interface, mark 11 as the primary interface, and then do the forwarding. Create an entry that make use of the port group as forwarding actions. So the other question that you're going to have is like, I just have one network. How can I like run the legacy MPLS applications and the new application together? So the answer is also very simple. So basically, in the previous example, we are talking about like a range for a defined range for Openflow MPLS, right, for the transport labels, and there is another range for the layer 2 VPN. So basically, we are going to define different range for different applications. So you have a range for existing maybe signal MPLS, like you have like RSVP use the range 1, L3 VPN use range 2, L2 VPN use range 3, and Openflow transport label use range 4, and Openflow layer 2 VPN use range 5. So in that case, basically you can have the legacy MPLS protocol to be run at the same time as the Openflow MPLS applications. So the other problem that you're going to see is like how ISSU can be done, right? So I think most of you come from like service provider background, and ISSU is something that is only work on the paper but doesn't work in the production. It's kind of like due to the fact that it's complicated, because the device needs to keep track of the routing state, and the peering router is not aware that this device is undergoing restart. So basically, I wouldn't say that anyone, like most of the service provider, basically won't turn it on during the upgrade. So with Openflow, basically we have a chance to actually solve this problem. This is because, like in Openflow, because all these routing signal state will not be kept by the network device. It will be kept by the control layers, right? So from the one device perspective, they are not aware about like if there is like control plane need to be changed or restart, then the network device will not be able to know about it. So it will keep forwarding and forwarding, right? So in the diagram, maybe you have an old release that need to be updated, and then in the middle stage, then it is restarted, and the new state and the new release will be in effect at the step number 3. So in that case, after the new release is active, then what is typically would do is try to retrieve the forwarding tables from the network device and to see if there is any need to update. So for the entire process, there is, like for the upgrade, there is nothing that will happen to the control plane, the forwarding plane. So that's why you can guarantee that traffic will start forwarding the same way before and after the upgrade. So now I want to summarize my presentation. Basically, there are a few things we talk about. So we talk about that network is no longer a standalone resources, so it has to work with servers. And as server get virtualized, network also need to get virtualized, right? So that's the reason why people are talking about SDN. They want to they want the ability to actually to have the network as service and the on-demand service, and the ability to tie the network service to the applications. And also we talk about like one of the challenges that you're going to see if you are trying to implement the MPLS in your WAN virtualization application. And we also talk about like some of the questions that you may have as you are trying to deploy MPLS Openflow in the networks. So thanks a lot. Thanks.
Any questions for Eric? No? Thank you. Thanks, Eric. So the last speaker on this panel is AJ, Alistair Johnson from Nuage Networks, and he'll be talking on branching out with SDN. AJ?
Hi, everyone. Oh, excuse me. Hi, everyone. Good afternoon. I'm here to talk about something that's actually really exciting to me. While I've been in Nuage Networks now for coming up on 9 months, before that I was in the business of building routers, and before that I operated routers and helped carriers operate routers. And for me, for a long time after the SDN noise popped up, it was more a case of still don't know what it can do for me. When I moved over to work for Nuage and started looking at what we had achieved in the data center and where we were going and what SDN brought to the table, I actually got really, really excited about this. I'd been very, I guess, conservative on where SDN would play value in carrier networks. But once I started to see how we could leverage all IP networks and leverage some of the capabilities that have been developed on a fairly open platform for data centers, I saw some really interesting opportunities for carriers to deploy SDN-based L2 and L3 VPNs in their network, which can solve a number of problems that we might be having with our existing approach today. SDN, as we know, is kind of new ways of thinking about existing ways of working. We've got this decoupled architecture around forwarding and control plane, separating hardware and software potentially, and often in cases, controllers, operating systems, and the underlying forwarding engines. So I'm not going to spend too much time on that. We know where we are with SDN. But looking at the WAN space, it's been pretty untouched for about 15 years. I mean, if we look at when RFC 2547 was first published, that was nearly, actually, well, 16 years ago this month. L2 VPNs, you know, they're coming up on fairly elderly as well. Nothing has fundamentally changed in the way that these services are delivered. We've done a few things. You know, we've dealt with scalability of networks. Routers have got bigger and faster. We've deployed more VRFs, more VPLSs. We've used different signaling technologies, but fundamentally the services have remained the same. At the same time, the CPE hasn't really changed, or the CE router. It's still basically the same device. It runs a routing protocol, it has a LAN port, and it has a WAN port. It's probably faster than it used to be, but that's about it. Nothing's really changed here. So when we started looking at software-defined VPNs, the concept of SDN for VPNs, we said, well, what if there was a new way of thinking about the smart edge dumb core? What if there was a way to change the CPE paradigm just as it's been done in the data centers, as Eric mentioned? What if there was a way to leverage cheap compute at the edge to have high-speed forwarding engines that are centrally controlled? What if we could solve some problems like delivering layer 2 services to a customer where we only have a layer 3 transport network? You know, for instance, over a commodity wireless network like a 4G network. And what if there was a way to do all of this operationally efficiently? So from a tech perspective, one of the key building blocks that's been happening in data centers, and that I think is very useful in what I'm going to talk about, is VXLAN. VXLAN is a IP encapsulation for Ethernet. Basically, Ethernet frame into a UDP packet into IP. We can run it over IPv4 or IPv6 underlay transport. We add a bit of overhead, so 8 bytes plus a UDP header plus the appropriate address family header. So plus minus 50 bytes depending on what you're transporting. It's totally routable over IP, so as long as we have an IP network, we can transport between endpoints. Anything that we do in an IP network, like ECMP, fast reroute, etc., will apply to an encapsulated packet. And I hinted at this last year when I presented at APRICOT about EVPN and the VXLAN data plane, about the fact that a VXLAN tunnel endpoint, or VTEP, could be a router, or it could be a server, or it could be something running on a server. And this is when I was starting to look at the way of delivering VPNs, direct compute resources. So the other big piece of tech that's really useful to look at is EVPN. I'm not going to rehash it. The nutshell, and it's now standardized in at least 2 cases. We have RFCs there that define the MPBGP architecture and the implementation over MPLS. But the red box there, network virtualization overlays, still going through almost at the end of the IETF process, to talk about using EVPN with a VXLAN transport. So EVPN lets us carry in the BGP control plane IP addressing, just like we do today in a classic L3 VPN, or a BGP VPN, or RFC 2547 or 4364, however you wish to refer to it. But we can also carry MAC address information. So we're not limited to just layer 3 services. We can provide layer 2 and layer 3 reachability information, so a hybrid service, which allows us to have a distributed layer 3 segment where all of the hosts look like they're on the same logical layer 2 network. Or it allows us to start at layer 2 and easily add layer 3 into the same service later on. And we can specify these next hops, where the subnets live, and a VXLAN transport identifier, the VNI. So, how do we put it together? EVPN is this control plane. It can distribute MAC and IP reachability information around your network. So we can scale this pretty neatly, right? BGP has scaled pretty well for IPVPNs and the internet in general. Federation is pretty easy. Route reflectors, confederations, I mean, anything that we do with BGP and the rest of the network, we can do for this address family. It's controllable. We have a very programmatic approach to the network topology. We can be powerful with our routing policies to determine how we exchange routing protocols and what this means for links and PE routers and eventually the edge devices for traffic engineering. And it's very efficient. We can deliver layer 2 and layer 3 services over a single interface. We can also handle redundancy and multi-homing in the protocol. And VXLAN, as a data plane, gives us this ability to deliver Ethernet frames over layer 3, as I mentioned. So in this case, our underlay transport could be an L2 VPN, it could be an L3 VPN, or it could be any IP network, the internet, a 4G service that you buy from another operator. So that your reach extends significantly in this way. So how could it look like? In this case, here's an architecture. And we've got a controller here which is going to program the forwarding table. So this is a BGP speaking SDN controller. It's programming Open vSwitch running on the CPEs. Open vSwitch is a community project for implementing a virtual routing and switching engine on commodity compute. We can calculate the overall forwarding topology of the network in the central SDN controller, and we can achieve basically calculate once, program many. This means that we don't have to have mass routing protocol adjacencies with every CPE, but it also means that we can do some topology hiding, and I'll talk about that in the next slide. What we do is we exchange traffic directly between the CPEs over the underlay transport network, whatever that may be. It could be the internet, it could be an IPVPN. And as I mentioned, the underlay network is no longer aware of the subnets behind the CPE. So if we look at the CPEs here, you see that we have these subnets sitting behind them, and potentially subnets with MAC addresses, a host in this case with a MAC address. We have WAN addresses. Now, when we are building this topology, the underlay network which is sitting behind it today, if this was a classic IPVPN, would need to be subnet aware. We would see at least 3 routes in the RIB for this VPN service. Now, this presents some interesting scaling problems for very large IPVPNs. One of the customers I've worked with has an IPVRF that's about 100,000 routes in the VRF. They're not carrying the internet. This is their corporate network. They have a very flappy network because it's so big. They have to run BGP damping in their VRF because as they go out to their actual VPN service providers, they were having such high levels of BGP updates that they were causing some issues on the service providers' PE routers. So for them, it gets really interesting, this concept that, well, my service provider only ever sees my directly attached interfaces, the PE to CE link. If I run a software-defined VPN over the top of the L3 VPN, my topology is now hidden. The provider edge routers are just seeing these CEs. We don't need to speak necessarily BGP from the CE to the PE anymore. And I can program my network forwarding table to all of these CPEs and run VXLAN over the top. Where this gets even more interesting is if I need to use multiple service providers or the internet or merge both of them together and build networks that span non-congruent underlay topologies. And of course, with these controllers, using BGP EVPN as the fundamental signaling protocol, we can federate out to multiple controllers to support the scale required. So this gets really interesting for both service providers and large enterprise network operators. I'm talking about networks that have at least 1,000 sites in a VPN, and this is not unusual. Any large multinational corporates in this kind of case. Alcatel-Lucent, Nuage's parent company, our WAN extends to over 1,000 sites. This is a problem that even we have in our WAN. Any service provider, I'm sure in the room, has large customers with very complex VRFs. And where this also gets very powerful for both the service provider and the customer is that we can start automating these changes so that we don't have to go and touch PE routers all over the place when routing topology needs to change. If I have a customer that makes a change to, or asks me to make a change to the VRF I host for them, that change might require me going and changing a routing policy on 100 or more PE routers to make sure that the change in VRF topology is reflected. If I can do that through the SDN controller, push it to the edge devices, that gets a lot more interesting. Now start imagining that for not just routing, but for things like ACLs. If I have a customer that says, block DHCP coming from my branch sites, well, that's now an ACL that needs to be configured on every PE router and every sub-interface facing the customer's branch. If we do that once in the SDN controller and push to many devices, we get a lot more acceleration in how we are managing this VPN. As mentioned, we can populate both the actual L3 topology and the L2 topology as well, which means that we can have, for instance, that 10.2.0.1/32 move over to another site, but maintain its layer 2 adjacency with hosts that were at the first site. From a data plane perspective, the CPEs forward directly between each other using VXLAN, as I mentioned. This is really just a slightly deeper look at what I've mentioned previously. And the underlay network is just seeing VXLAN. So the underlay no longer needs to be VRF aware. We could deliver this on just an internet edge router. Or this could be an enterprise consuming just internet services. The data plane can obviously be further encapsulated if we need to. So if we need to make the step towards confidentiality, we can wrap it in IPsec. It's just IP. It's a routable protocol. It's not MPLS. So this gets pretty interesting. So from a flexibility perspective, I was looking at this a lot, and when people say to me, okay, this sounds interesting, but it's complex. It is complex. Make no mistake about that. but it simplifies the network topology. The service provider needs to know less about the customer's network from the actual edge networking perspective. We take a lot of the intelligence out of these routers and move it right out to the edge, where a lot of the complexity had to happen anyway. And we can leverage some of the common things that we do in broadband networks. Rather than statically numbering our CEPE interfaces, why don't we use DHCP? So the CPE can boot, get its WAN address, attach to the VRF if it needs to, connect to the SDN controller, receive its forwarding plane. We can increase the flexibility by using different assets in our network. If I'm a massive service provider, I probably have a residential broadband division, a business VPN division, a wireless division, and the network assets are probably quite separated, which means if I want to consume different access to interfaces and build a mashed up network of different access interfaces, it's complicated and expensive for me to do that. If I treat my VPN service as just another IP packet on any of my networks, building a hybrid overlay makes life a lot easier. We can touch far fewer parts of the network and allow the devices to handle the end-to-end data plane. One of the other big value use cases here is enabling service chaining. This is something that if you've played in the data center space with SDN, virtualization, and NFV, you've probably heard about. This slide has about 1 million animations, so I'm going to zip through them so we can stay on time. So what service chaining allows us to do is have these virtual functions sitting somewhere in the network, the data center perhaps, central compute sites, serving POPs, etc. Virtual firewalls, virtual load balancers, DPI, DDoS mitigation scrubbers, etc. And we can, in the data center today, it's very common for SDN to be used to define where we want to pipe traffic through. Oh, my public-facing web servers must be accessed through the virtual firewalls and the virtual load balancers before it hits the public web. So we can apply that same approach. Rather than having to do complex PBR rules, we can do service chaining. Say, okay, traffic from CPE number 1 to CPE number 2 must first pass through this virtual network function. Again, VXLAN means that we can selectively program a forwarding rule that says pick up this traffic and shift it over to this endpoint and drop it off, which could be at the hypervisor hosting a virtual function, or it could be the appliance or the virtual function itself if it's a VXLAN VTEP. Meaning that adding inline services to a customer's network, or their own network if they're doing this themselves, gets really easy. One use case that I've seen come up time and time again is network analytics. If I have a site or 2 sites which are complaining of poor performance, maybe I want to mirror the traffic and perform some kind of analytics on it. So I can do this. I can just say mirror the traffic, send it over VXLAN, drop it off at my analytics box. This could be, redirect the traffic through that analytics box or DPI engine and take an action. Feed something back to the SDN controller to do something new after traffic is determined. So, maybe you're thinking now, this sounds pretty neat. I do want to do this, but I've got this existing network. How do I get the two to talk? Well, the cool thing is, and we talked about this a year ago, and I know Eddie spoke about what Juniper was doing, I spoke at the time about what Alcatel-Lucent was doing, and many other vendors have sort of joined the overall party to get EVPN support into the industry standard PE routers that we run in our networks across all of the large vendors, and also to support VXLAN data plane, which means that we can, because this is BGP, it is EVPN, it's VXLAN, we can terminate traffic into an existing PE router and bridge these new CPEs with the old networks if we need to. Or we can bookend and take traffic out of the overlay network and drop it off as a sub-interface towards an existing PE router. This is a little bit more seamless, but requires some functionality in the PE. This is a little bit more complicated to implement, but you can avoid changes, software upgrades if potentially in the PE routers. Both approaches do work. whoops, I was supposed to delete that slide and replace it with that one. So if we look at the two approaches, one of the key things that people sort of start thinking about is, oh, overlays are a bit scary. But when you really look at it, we've been doing overlays in many parts of the networks for a long time. MPLS is effectively an overlay technology. It certainly wasn't the first one that came around. But we've got overlays on the left-hand side, we have overlays on the right. We can move away from services constrained by where our networks physically exist. Out of curiosity, who's brought up an MPLS NNI before in the room? A network-to-network interconnect, option A, B, or C? One person? Two people? Is it easy to do? Or is it complicated? Yeah, option C is pretty complicated, but option C is the most sort of seamless approach. So if we're trying to extend service reach through MPLS NNIs like option C, it's complicated. Now, I used to make MPLS routers. I know it's complicated. So we can extend network reach in the MPLS paradigm with NNIs, but it's easier to do it at IP, because then we don't care anymore about these complicated NNIs. We call them peering points, internet exchanges, much more straightforward. So the service goes where IP is available. We have this, today, highly distributed topology and control. We move to a centralized control, but distributed topology. So this, to many people, is scary, but when you start looking at the scale of data centers and the scale of enterprise WANs, you realize that there's actually a reasonable amount of overlap, and there are things that make a lot of sense to centralize. I was skeptical of this at first. I've slowly over time become convinced because I've spent a lot of time looking at this. Both of these are very high performance approaches, and hopefully someone should challenge me on this and say, but what about the MTU impact of adding that extra 50 bytes? It is a good question. Dealing with fragmentation in the data path is expensive, but if we're engineering our networks happily for the, where are we, 2015, maybe we can start to push some of our networks, at least for on-net services, to higher MTUs. Many people can do that today, so fragmentation doesn't become a big deal. So we are still handling the packets pretty efficiently, much more flexibly as well. For me, one of the real unique use cases here is saying, I need to get a layer 2 VPN into this room using a 4G interface. Today, that's nearly impossible. Using VXLAN makes the data plane a trivial approach. Yeah, it's kind of inefficient, but we can get the traffic there. And with centralized control, we can do that 1,000 times, over and over and over. So this is where the power really comes from. And today, we do PBR, policy-based routing. It has its limits, especially if we're doing it on an IP and by IP basis. Being able to put it into a VXLAN tunnel and drop traffic straight off at a virtual network function is very, very powerful. So in conclusion, I really think that SDN has actually found some proven use cases in the DC that make sense. A lot of these use cases, once you start to look at them and start removing some of the data center clouds and draw a service provider network underneath, start to overlap. This is not just experiments anymore, and it's not just, oh, we're doing the same thing but a little bit differently. This really is a rethink of the delivery architecture, but it's real. Overlays are not new. We've been doing them for years. It's nothing particularly scary. And this service layer sort of overlay is really the direction that networks have been evolving to for a long time. It puts the smarts right at the edge. It leaves the signaling protocols in the core for doing traffic engineering, can simplify a lot of what we're doing in the service provider network. And there's real use cases for this for everyone. So thank you. I hope this was useful, and I hope they didn't stand in the way of lunch.
Any questions for AJ? No? All right, so thank you once again, gentlemen, for your time, and thank you guys for